Hello everybody, this is going to be the video for pages 21 to 23. I am not going to be recording on how to actually answers for each one of these. The answer is going to be in the on Schoology and answer keys. I am, however, taking the time to make sure that you have a video of a step-by-step explanation as to how we got the setup. So this video will solely be for setup. I hope that this angle of approach to solving these problems is helpful because we haven't done this before in the past. And again, if it can be improved, please let me know. That way we can benefit you guys and benefit other students. And in the future, here we go. Oh my gosh, I'm looking at my sweatshirt that I'm wearing right now, and my daughter, she was laying on me earlier, just got snot all over it. It is disgusting, but that's neither here nor there. Let's get going. Okay, I'm going to just set up each one of these. And this is on page 22. Okay, before I actually wasn't ready, but now I'm ready. So let's do it. We're going to go over every single one of these. Then I'll tell you what you should do after you're done watching the video. We're already a minute 20 in, so I'm going to try to go over how to explain each one of them in about under 2 minutes per for all 14 problems. Let's see how I do. Number one, a certain calculus student hit Miss Schwartz in the head with a snowball. Not very nice. Not very nice. That student is no longer with us. Makes sense. That makes a lot of sense. If the snowball is melting at the rate of 10 cubic feet per minute, at what rate is the radius changing when the snowball is 1 foot in radius? And then in problem number 2, at what rate is the radius changing when the snowball is 2 feet in radius? Answer should be expressed in terms of feet per minute. Please notice that I get a little bit angry when I think about this. Please note that if you are not taking the time to include your units, then that could be lost points for you that were easy. Okay, so that's number one. If you're forgetting that, oh man, that just means you dropped the ball and you could have done a lot better. Easy points you should always go for, and that's all I'm going to say. So let's look at what we have here. A certain calculus student hit Miss Schwartz in the head with a snowball. Neither of those sentences are relevant. I'm just going to cross those out. Not relevant, not relevant. Okay, now it says a snowball. A snowball's a sphere. So, took care of that one. A sphere. Okay, a sphere has two things that come to mind. The volume is 4/3 pi r cubed, and I don't know what they want yet. The surface area is actually the derivative of 4/3 pi r cubed, which is 4 pi r squared. Okay, so those are just two formulas that you may find useful if you need to do the problem. It's melting at the rate of 10 cubic feet per minute. Now, that cubic feet per minute part, that's the huge key. That's a rate. If that's a rate, that tells me that that's d something dt. Cubic feet tells me that it's volume. So because I have cubic feet per minute, then dv dt must equal 10. And if you take a look at the variables here, it kind of makes sense actually why that works. We have volume, which is cubic feet, and then we have time, which is minutes. So dVt does make sense that it's 10. Okay. Excuse me. At what rate is the radius changing when the snowball is 1 foot in radius? So notice there's that last part there with that 1 foot in radius. That 1 foot in radius, that's r equals 1. Do not use that until you have the derivative. Use only for derivative. Now, sometimes you will have to use them in the original equation just to solve for another unknown, but when you're taking your derivative, though, you're looking and seeing what's changing, what two variables are related to one another. So just to reread the question to see what the question is asking here, it says, at what rate is the radius changing? Freeze, that's a dr dt. So I want to know what the rate is, the radius is changing at with respect to time. Oh, and then for problem 2, is what rate is the radius changing when the snowball is 2 feet in radius? Okay, so what I'm going to do here, and again, I'm not going to solve the problem for you, is I'm going to take volume equals 4/3 pi r cubed. I will not be using the surface area equation because I want dv dt. I'm going to take the derivative with respect to time, and I am looking for what dr dt is when r equals 1 and dvt equals 10. You should be able to take it from there. Be careful with the 4/3 pi when you take your derivative. 4/3 pi is just a coefficient. Do not do a product rule. Your dv dt, just because I'm scared that you're going to not listen to me, is 4/3 pi times whatever the derivative of r cubed is, dr dt. That's all I'm going to do for you. The rest of the work is on a paper for you. And again, r equals 1 is going to be for problem number 1. And r equals 2 is for problem number 2. Okay, next one. Oh my gosh, it took 5 minutes with that. Faster! Baseball diamond is 90 feet square, not 90 square feet. If you haven't tried the problem, you should probably pause and try before you're just watching how to do things. Again, think for yourself before you actually try to get some help with it. Mr. Lakin runs from first base to second base at 25 feet per second, which sounds pretty fast. How fast is he moving away from home plate when he's 30 feet from first base? How fast is he moving away when he's 45 feet from first base? Okay, so same idea here is they give you 2 separate problems in one. Let's get a diamond here. So we got 90 feet square. We'll call this home. We'll call this first, second, and third. Okay, it's 90 feet square. 90 feet square means that I am going to have this side be 90 feet. Check, and I drew a diamond. All right, I'm running from first to second at 25 feet per second. So here I go, I'm running. That's the change in x. So my dx dt is going to be 25 feet. How do I know that this is going to be 25 feet? How do I know that's dx dt? Is because I am changing, it gives me a rate, number 1. And every time they give you a rate, that's a derivative. So feet per second is going to be always a d something dt. And actually, I drew that wrong on my picture, so let me pause and fix this. Since I'm going from first to second, I made that dy dt instead of dx dt because I'm going vertical now. How fast is Mr. Lakin moving away from home plate when he is 30 feet from first base? Okay, so 30 feet from first base means I'm right here. And I've got from home, I'm right here. So from the catcher, that's where I am right now. But I'm changing though. So there's a couple things that are changing here in this picture. And if you're not sure what I'm talking about, let me draw this for you as to what I'm looking at. I see this shape here. I see that and that. I see a triangle. And what I'm interested in this triangle is how this value, this blue part, because right, how fast is he moving away from home plate? So this part is going to keep changing as I run to second base. So I have 2 variables that are related here. And I can start setting that up. If I call this y and I call this z, then I can say that 90 squared plus y squared equals z squared. This is an equation that relates to the 2 variables, my position from first base, and then also my position to from where I am running to home, the z value. I should note that this is a 90-degree angle. Now I want to note that this 25 feet should be a positive value because it says I am running from first to second. And since I'm running from first to second, my distance from first to second is increasing. And whenever I have a value that is increasing, its derivative should be a positive value. Again, what you would do from this step is take the derivative with respect to t on both sides. And I believe it told you locations. So one value be where y equals 30. So when he is 30 feet from home base, 1 is y equals 30. That's going to be for problem 3. And then for problem 4, it looks like y is going to be 45 feet. So there'll be 2 different answers here again. And let me just complete this other derivative, and we'll move on to the next 2 problems. Okay, or 1 problem, 5. Water flows into cubic feet per minute into a cylinder with radius 4 feet. How fast is water level rising when the water is 2 feet high? Okay, cylinders. The volume for a cylinder is going to be pi r squared times h. Okay, pi r squared times h. Now it says water flows at 8 cubic feet per minute. Per minute. Per minute. Per minute. Per minute. Per minute. Why am I getting excited? Because cubic feet per minute means that is volume. 8 cubic feet per minute tells me that this is a dV/dt. So that's number 1. I got cubic feet per minute. Okay, now I got my cylinder parts. Let me check that off. I did this part. I did this part. Water flows. Who cares? Radius is 4 feet. Okay. I may need that now. I may need that. But really, I'm going to have to plug that into the derivative for sure. So I'll put radius is 4 feet. Got that? How fast is the water level rising? Okay, when it says how fast, that is something, that is a rate. That means that you are looking for a derivative value when the water level rises. Okay, well, we'll call water level h. So the question is asking for dH dt. And when the water is 2 feet high, okay, well, that's helpful. H to be 2. Notice I do not care what the volume is when the radius is 4 and h is 2. What I do care about is what the rate of the volume is changing at. So the equation that I need is going to be right here. Volume equals pi r squared times h. And that is going to be how the radius and the height are changing for the volume. However, huge idea. Okay, I want you to think of a cylinder, and I want you to think of filling something up in the cylinder. Now, when you're filling something up in a cylinder, let's do filling up cylinders. Only one variable is actually changing. And if you don't know what I'm talking about, work. Come on. Show me how to fill up a cylinder.
1 by 1.
Yep. That's not what I want.
Make sure it's nice and snug.
That's not really what I want. But here's the idea. The idea here is that when you're filling up the cylinder, the stuff starts out at the bottom and then starts going up. Something's not changing. Why is that relevant? If you don't identify that right away, then what you're going to get is a product rule. Product rules will sometimes happen with these, but it's really annoying, and I like to avoid them. Avoid at all costs. I like to make the problem simple on myself. So how am I going to make this simple on myself? Well, I am actually going to plug in one value. And again, my general rule is sometimes I usually never plug in a value until I have the derivative. But if I see a product rule, I want to plug something in. I want to see if I can plug something in and make my life easier. The volume equals pi times 16 times h. 16 was r squared. So now my volume is 16 pi h. Why is this better? Because my radius doesn't change when I fill something up. Only the height changes, which means that dr dt here is actually equal to 0. So now I have a much better equation that relates my volume and height, and I can take the derivative and solve for what they're looking for. Really tricky problem, but again, really helpful to know. Use a product rule only when you absolutely can't need to. Otherwise, avoid it at all costs for related rates problems. If you see that there's a variable that is not changing with respect to time, substitute that thing in the original equation. 6 and 7. Suppose the Lake Forest High School swimming pool is in an inverted cone. Oh, the cone problems. Love them. All right, let's do a cone. Here's the cone. Okay, with height 20 meters. All right, so here's the height is 20. And radius is 5 meters. Okay, here's 5 meters. Okay, so I got 20, I got inverted cone, I got 5 meters. By the way, if you didn't know what an inverted cone was, and you drew it the other way, you'll still be able to get the problem. Inverted cone just means that it's not right side up or upside down or whichever you think inversion is. It is being filled with a hose, as it always is, which pumps in water at the rate of 3 cubic meters per minute. 3 cubic meters per minute! 3 cubic meters per minute! Cubic meters per minute. Cubic meters. Meters cubed. 3 of them per minute. dVdt. Okay, if I'm talking about dVdt, I need volume. My volume is 1/3 pi r squared h. That's my volume for a cone. Are we giving you formula sheets? Absolutely not, so you should know that. Volume is 1/3 pi r squared h. Okay, first thing, before I even finish the problem, and I use this information, so let me put a little check mark there. Before I even finish the problem, I notice that if I have to take a derivative right away, product rule. So I want to substitute something in. Again, product rule here, don't really like product rule. It's annoying. It's horrible. It's the bane of my existence. Blaine's bane. Avoid at all costs, and I think we'll be able to avoid it, but it's going to take a little shenanigans. Avoid at all costs. That says costs. Salma. Okay, now, when the water level is 2 meters, we'll come back to this. So we'll come back to how to avoid that. When the water level is 2 meters, so height is 2, how fast is the water level rising? Again, water level, that's how fast, that's dH dt. So that's what we want to know. We want to know dH dt. I don't know what R is. Sorry, I know what R is. I don't know what dr dt is. And I should be kind of curious about that because if I take a product rule, I'm going to need dr dt. All right, here's the trick. The trick for these problems is when you are filling up the cone, before you get to the top, there's another triangle right here. And they're similar. Oh my gosh, we have similar triangles. Mr. Lakin, you're sounding so annoying. I know. I am being very annoying. So here's what I mean by that. Because these two triangles are similar, you can set up a proportion. So for any h and any r, you always know, so let me draw these two triangles separately for those of us that don't remember a trig. For any h and any r, that triangle always has to be similar to the bigger triangle that has a height of 20 and a radius of 5. Okay, well, if that's true, we can set up a proportion with h over r is equal to 20 over 5, which means h is equal to 4r. That's excellent. Now, one thing I do like to do, even though it's not necessary for this problem, is I do take the derivative of each one because I have seen problems where they ask me for the rate of the radius, but they only give me height information. This tells me that the height is changing at 4 times the rate that the radius is changing at. Okay, now again, we won't actually need this for our problem, but we do need this part, the h equals 4r part. This one is super important, h equals 4r, because now I can plug everything back in to what I need. Now, I have h equals 4r, but I want dH dt, so actually I really want 1/4 h equals r. So let me change this here. I'm going to take this statement and I'm going to say 1/4 h equals r, because I want my volume in terms of h, not r. Okay, so now I have no room to write. Volume equals 1/3 pi r. R is 1/4 h squared times r. Well, if I simplify that, I get 1/16 times 3, which is 1/48 pi, Mr. Lincoln, you have a mistake. I want extra credit. No, I caught my mistake. Here, this should be an H, and this should be a H as well. So H cubed is how many H's we have because of the two H's in the parentheses here, the two H's with an extra H gets to three H's. Super tricky. That's the equation that you want to take the derivative of. That is an equation for a cone that uses similarity to get a volume and height related to one another. So when you take their derivative, you can see how their rates are also related. Now you have enough information to solve the problem. Tricky problem. 8 and 9. A stone is dropped into Lake... Oh my gosh, I'm already at 20 minutes. A stone is dropped into Lake Michigan and causing circular ripples. Of course they are. Whose radii increase by 2 meters per second. 2 meters per second, 2 meters per second, 2 meters per second radii. Okay, so let's go ahead and just do a dr dt equals 2 meters per second. Okay, how fast is the disturbed area growing when the outer ripple has a radius of 5 meters? Okay, so I have area. Well, the area of a circle is going to be pi r squared. And that's a slam dunk. How fast is the area? So how fast is the area is going to be dA dt. That's what you're looking for. And it looks like you're given two parts. One were 5 meters. How fast is the radius? Hold on, I'm confused as to what this problem is asking for the problem number 9. Anything about me, I always overthink a problem, and that's why I was stuck. How fast is the radius increasing at the moment? You already know that. So that one should be an easy one. All right, problem number 10 and 11. A fish is being reeled in at a rate of 2 meters per second. Oh, boy. Now, if you've never gone fishing, the reeling part is this part. So this part is 2 meters per second. We'll call that Z. dz dt equals 2 meters per second. By a fisherman at a river. Cool. If the fisherman is sitting on the dock 30 meters away, how fast is the fish moving through the water when the line is 50 meters long? All right, let's simplify. Let's simplify this picture, and let's also pretend that on a test you would not be given the picture of how to do this. So make sure you're aware of what the question is asking. Okay, simplified. We have this. We have Z. We have 30. That fish is moving in. Okay, so let's go back here. The rate we got. Let's check that off. Fishing line is being shortened by 2 meters per second. Now, if it's being reeled in, then that means that dz dt is actually a negative 2 meters per second. Because the length of that line is decreasing. It's being shortened. And whenever we have a function that is being decreased, its derivative should be negative. If the woman is, okay, got that part. So got the 30 meters above part. Okay. How fast is the fish moving when the line is 50 meters long? Okay, so then x is 50. We'll call this distance x. That's for problem 10. And then for problem 11, how fast is it when the line is only 31 meters? Let's back up. Both of these said when the line is 50 meters and 31 meters. That's when z is 50 meters and 31 meters. Okay, so that's going to be a 11. Now, we need an equation that relates these. Notice the height of the woman does not change. So this is a zero derivative. That 30 is not changing. X is changing, though. Z is changing. So let's go ahead and get an equation here. An equation could be x squared plus 30 squared equals z squared. Who really cares what 30 squared is? Not me. Because when I take the derivative with respect to time, the 30 squared goes away. It's 0, which is what we wanted. Okay, that should be it for you here. Hold on just a second here. Oh, I see what they're doing here. When you take the derivative, you're going to need an x value. How are you going to get that x value? Because when I take the derivative here, I'm going to have 2x dx dt equals 2z dz dt. Okay, and I know what dz dt is. And I know what z is. I'm looking for dx dt. I don't know if I said that before. It says how fast is a fish moving through the water. So that's going to be for both of these. I need dx dt in both cases. But I don't have x. So the way I get x is I have to do two separate triangles where one side is going to be 50 and where one side is going to be 31. You're going to need to use Pythagorean theorem to get each one of these. Okay, that's it for this one. 12. A student at Lake Forest is standing at the top of a 25-foot ladder. Irrelevant. 25-foot ladder. Okay, so here's a ladder. 25 feet. Not changing. So this is a zero derivative. She was horrified to discover that the ladder began sliding away, as they always do in these kind of problems. Sliding away from the base of the school. Here's the base of the school at a constant rate of 2 feet per second. Okay, feet per second. Feet per second is going to be a derivative. Now, if we call this value x, then dx dt is 2. Positive or negative? Let's see here. How do I know that? Okay, positive derivative is when something is increasing. Negative derivative is when something is decreasing. My distance, the base is moving away from the wall. That means I'm going to have a positive 2 feet. Got it. At what rate was the top of her ladder? So let's call the top of her ladder y. Let's check some stuff off. So we use 25 feet. We use sliding away, the base of the school, constant rate. At what rate was the top of the ladder carrying her? Okay, we got that. When the base was 17 feet away, so it looks like x is 17. Okay, when x is 17, well, it looks like you can solve for y with the Pythagorean triplet. Again, you're not really going to use those until your derivative. But you'll need to solve for y right away, though, just to get what the y value actually is to plug into the derivative. An equation that relates these three ideas here will be Pythagorean theorem with an x squared plus a y squared equals 25 squared. And as before, once you have your variables related, you can take the derivative to see how their rates relate. And again, you're taking the derivative with respect to time. And that should be all that you need for that problem. I did not take care of this last part. I think I've been dropping the ball on that in both problems. I get so excited I miss the point of what I need to do. The rate at the top of the ladder is going to be dy dt. I am looking for dy dt. And please tell me this is the last one. Oh my gosh, 2 more. Okay, spherical balloon. Okay, well, I just gave you the formula for that. That's going to be volume equals 4/3 pi r cubed. Okay, losing air, okay, at 5 cubic inches per second. So that means dv dt equals negative 5 inches cubed per second. Again, I knew that was the rate because it said inches per second. I didn't get excited about it. Yeah, that's right. I want to go back to number 1. I want to check something because I want to make sure I didn't mistake anything. Yeah, I did. If the snowball is melting, oh my gosh, clumsy Mr. Lakin. If it's melting at the rate, that value should be a negative value. Shame on me, Mr. Lakin. For those of you that caught that, good job. Hope I don't have any other mistakes. Too late now. If I do bring them to my attention, first one that will get some extra credit if I made any mistakes in the video. Okay, volume equals 4/3 pi r cubed. I have my radius and how it's related to the volume, so that's good. I have dV/dt is -5. At what rate is the raise of the balloon decreasing? So if it's asking for what rate is the raise decreasing, that means that I'm going to be looking for dr/dt, and that value should be negative because the radius is decreasing. And that makes sense. If your volume is decreasing, your radius should not be increasing, right? Because your volume is only dependent on your radius. Okay, and then it says when the radius is 5 inches, so r is 5, and you're home free. Take the derivative with respect to time for both of these. 14. Oil spills into a circular pattern. Great, got it again. Radius is increasing at 3 feet per minute, so the raise increases. We have dr/dt equals 3 feet per minute. A positive 3 feet because we have increases. How fast is the area? So how fast is the area is going to be dA/dt. That's what we want at the end of 10 minutes. So, oh, that's a little bit different. I like it. Okay. This is a little trickier. Let's set up what we know. Area is going to be pi r squared. If I take the derivative right off the bat with respect to time for both sides, I find that the area relates to the radius by finding 2 pi r, because that's the circumference, and then multiplying that times the rate that the radius is changing at. Now, if I look to what I can plug in here, I'm looking for dA/dt. I don't have an r value, but I do have dr/dt. Dr/dt is 3, but I need an r. So what is my r value? Well, it says that r is increasing at a constant rate of 3 feet per minute. Okay? And you can assume that at the beginning, there was no radius of a circle. So at 3 feet per minute for 10 minutes, so r is 3 feet per minute for 10 minutes. Well, that's going to give me, over 1, that's going to give me 30 feet. Okay, so your radius is 30 feet. And now you have enough information to be able to solve the problem. That was slightly trickier. I like it. A little curveball. If you stayed through watching all of this, thank you. I really appreciate that, and I hope it helped. If it didn't, please let me know how I can improve. What I would recommend when you're all done, I would recommend practicing. These practice pages start on page 34. Keys for everything is online. We organized them last year and provided answers for you for every single one of them by difficulty level. So these are AP style questions. These are very difficult, challenging questions. So again, try as many as you can. The more you do, the better you'll be. And I hope that these videos have helped you. Good luck.